Hello, so this is the second module in this series and the topic is mean convergence. So in order to set the stage for discussion of mean convergence of Fourier series, let us introduce some notations and terminology. So first we define the notion of norm, the L2 norm of a function g. So again let's begin with a integrable function g from ab to r, and its L2 norm we define to be norm g equals integral a to b mod gt squared dt, the whole thing raised to the power half. That is equation 2.1 that you see on the slide. However, the integral that you see in 2.1 may actually diverge. It may take the value plus infinity. For example, let's take the function g of x equal to 1 upon square root of x. It is integrable on 0 to 1, right? So integrate 1 upon root x, you get square root of x times a constant. Put the limits 0 and 1, you get a finite value. So 1 upon root x is integrable, but its square, namely 1 upon x, is not integrable. So this particular gx equal to 1 upon root x is integrable on 0, 1, but not square integrable. The square of gx is not integrable. So we must now cut down the class of integrable functions to a subclass. And let's look at this subclass, the space L2 of AB. The space of all functions for which the integral 2.1 is finite is denoted by L2 of AB, and it is a vector space. How do you check it's a vector space? It should be closed under addition and multiplication by scalars. That it is closed under multiplications by scalars is quite evident, because if f is in L2, then c of f is also in L2. Namely, if f has finite norm, then c times f will also have finite norm. That part is pretty clear. What we need to prove is that if f and g are square integrable, then f plus g is also square integrable. Let us quickly run through the proof of this. Mod fx plus gx squared, which is less than or equal to mod fx plus mod gx the whole squared by triangle inequality. Let us expand it. Less than or equal to mod fx squared plus mod gx squared plus twice mod fx into mod gx. Now use the fact that 2ab is less than or equal to a squared plus b squared, and you immediately get that mod fx plus gx the whole squared less than or equal to twice mod fx squared plus mod gx squared. Now what do we know? Integral mod fx squared is finite, integral mod gx squared is finite. So integral of mod fx squared plus gx squared is also finite, and twice of a finite number is again finite. So integral of mod fx plus gx the whole square is finite. In other words, f plus g is in L2 of AB, and the verification that L2 of AB is a vector space is thereby complete. Now we come to a very important property of this vector space L2 of AB. It is an example of a complete metric space. So what does that mean? That's stated in theorem 14. L2 of AB is Cauchy complete with respect to the norm. What does the last clause means? What does Cauchy completeness mean? Let us take a look at it. So suppose if you take a sequence Gn of functions such that norm of Gn minus Gm goes to 0 as Nm goes to infinity, then there is a G in L2 such that norm of Gn minus G goes to 0 as n goes to infinity. In other words, every Cauchy sequence converges. That's the meaning of this sentence. We shall not prove the theorem 14 because it's quite a standard result in analysis, and I have given you a reference. The best reference in my opinion is this book of Goffman and Pedrick, a first course in functional analysis. I already indicated this in the list of references, and so I'll just assume this theorem. Now, why can't we simply work with continuous functions? Why do we have to introduce this space L2 of AB? Why not just take the set of all continuous functions on closed interval AB and work with it? There is going to be a problem. Suppose if you take a sequence of continuous functions on AB such that the norm of Gn minus Gm goes to 0 as Nm goes to infinity, it may not be the case that the Gn converges to a continuous function G. In other words, you got a Cauchy sequence of continuous functions, which is Cauchy with respect to the norm 2.1, but the limit function G may not be continuous. The limit function G is in L2, sure, but it may not be continuous. So we cannot restrict ourselves to the class of continuous functions. That's why we need to introduce this special vector space L2 of AB. Cauchy completeness is essential for many important existence results in analysis. Another pleasant feature is that L2 of AB is an inner product space. There is an inner product, namely inner product Fg equals integral a to b Ft into Gt dt. Now, we are tacitly assumed that we are working with real valued functions. Nothing stops us from taking the functions to take complex values. So, if f and g are complex valued functions, then we must put a bar on the second factor in the integrand gt. We should then define the inner product of f and g to be integral a to b ft gt bar dt, the bar denoting complex conjugation. What is the inner product of g with itself? Inner product of g with itself is integral a to b g bar dt or g dt if we work with real. In other words, norm g squared is exactly integral a to b mod gt squared dt, which is nothing but the inner product of g with itself. Now, here are some easy exercises for you. First, prove the parallelogram law. Norm of f plus g squared plus norm of f minus g squared is twice norm f squared plus twice norm g squared. Why is this called a parallelogram law? You should think of the norm of f minus g as the distance between f and g. So, if you have a parallelogram ABCD, then you know that AB squared plus BC squared plus CD squared plus DA squared is twice AC squared plus twice BD squared. The sum of the squares on the four sides of the parallelogram equals the sum of the squares on the diagonal. Next problem is the Pythagoras' identity. Norm of f plus g squared is norm f squared plus norm g squared provided f and g are orthogonal. When are f and g orthogonal? We say that f and g are orthogonal if the inner product of f and g is 0. So, when you have two orthogonal functions f and g, norm of f plus g squared equals norm f squared plus norm g squared. Finally, the triangle inequality. Norm of f plus g less than or equal to norm f plus norm g. These are easy consequences and they hold in any inner product space. This is probably familiar to you from basic linear algebra courses. This is basic linear algebra. This has nothing to do with analysis. The last exercise in this slide is show that 1 comma sin x comma cos x comma sin 2x etc. forms a orthogonal system of functions on minus pi pi. If I take any two of them, if I take any two distinct ones and I take the product and I integrate it from minus pi to pi, I get 0. Cos jx sin kx, when I integrate from minus pi to pi, I get 0. Cos jx cos kx, when I integrate from minus pi to pi, I get 0 when j is not equal to k, etc. So, it is a orthogonal system of functions on minus pi pi. Let us look at other types of orthogonal systems. Let us look at the interval minus 1 1 and let us take L2 of minus 1 1. Here on the slide in equation 2.3 there is displayed a polynomial. Pnx is the nth derivative of x squared minus 1 to the power n. Note that x squared minus 1 to the power n is a polynomial of degree 2n. When I differentiate it n times, I get a polynomial of degree n. Of course, when n is 0, you are not differentiating at all. You are simply not differentiating, and you have got x squared minus 1 to the power 0 is simply 1. So, P0 of x is 1. Now, you observe that the degree of Pn x is exactly n, and so you got a linearly independent set of polynomials P0x, P1x, P2x, etc. These polynomials are pairwise orthogonal. If I take Pnx multiplied with Pmx, integrate from minus 1 to 1, you get 0 if m is not equal to n. Here are again some elementary exercises. Show that Pn of 1 is 1. Next is Pnx is an odd function if n is odd, and it's an even function if n is even. And the last part is show that this polynomial Pnx has n distinct real roots in the open interval minus 1, 1. These polynomials are extremely important in analysis, and they are called the Legendre polynomials. And the zeros of these Legendre polynomials, the roots of these Legendre polynomials which lie in minus 1, 1, they are important in numerical integration or numerical quadrature. It's called Gaussian quadrature. You can see the book of S. Chandrasekhar for more details on this Gaussian quadrature and how he applies it in quantum theory and radiative transfer. Now let us take the next result on the least square approximation. So before we take up the meaning of least square approximation, let us make a definition. You take a finite linear combinations of sines and cosines as displayed there. I have taken 1 sin x, cos x, sin 2x, cos 2x, etc. sin nx, cos nx, and I take a linear combination. What do I get? Alpha naught plus summation j from 1 to n alpha j cos jx plus beta j sin jx. That expression has been denoted by Qnx. Qnx is called a trigonometric polynomial of degree at most n. So that's a definition of trigonometric polynomial. So if I take a Fourier series, and the partial sums of a Fourier series are obviously trigonometric polynomials. That's what is stated in the slide. The nth partial sum Sn fx is again a trigonometric polynomial of degree at most n. And we would like to compare the norm of fx minus Qnx with norm of fx minus Snx. The following theorem asserts that if Snx is the nth partial sum of the Fourier series, then this f minus Snx norm is going to be less than or equal to norm of fx minus Qnx. In other words, Sn fx is the best possible approximation to f among all trigonometric polynomials of degree at most n. Let's go to the next slide. Here you see the result stated in the form of a theorem. Suppose f is in L2 of minus pi pi and Qnx is a trigonometric polynomial of degree at most n. Then norm of fx minus Sn fx is less than or equal to norm of fx minus Qnx. Equality holds if and only if Qnx equals Sn of fx. So we also have a case of equality. Okay, so let us begin with a simple and trivial equation. Fx minus Qnx. I add and subtract Sn fx. So I am looking at fx minus Qnx equals fx minus Snx plus Snx minus Qnx. The second part, Snx minus Qnx, is been abbreviated to Rnx. So Rnx is a trigonometric polynomial of degree at most n. Now we shall show that this piece fx minus Snx is orthogonal to each of the functions 1 sin x, cos x, etc. up to sin nx and cos nx. If I show this, suppose I show that fx minus Sn fx is orthogonal to each of these things, then what do I conclude? It will mean that it is also orthogonal to the linear combination. If something is orthogonal to u and it is orthogonal to v, it will be orthogonal to u plus v, it will be orthogonal to u minus v, it will be orthogonal to alpha u plus beta v. So fx minus Sn of fx will then be orthogonal to a linear combination of these things, which means it will be orthogonal to Rnx. And then I can apply the Pythagoras' theorem. That is the strategy. So let us now begin. Cos jx is orthogonal to 1 sin kx and cos kx when k is not equal to j. So let us now calculate the inner product of fx minus Snf with cos jx. I'll get two terms. One is integral minus pi to pi fx cos jx. But what is that? That's exactly pi times aj from the formula for the Fourier coefficient, remember? And the second piece is what? Integral minus pi to pi Sn fx cos jx. Now, Sn fx is a linear combination of sines and cosines, and cos jx is orthogonal to everything other than itself. So the only term that will survive in the second integral will be the aj cos jx term. You will get in all minus pi to pi integral aj cos squared jx. The cos squared jx has to be written as 1/2 of 1 plus cos 2jx. That's what I had done in the slide. And what do you get? The cos 2jx term integrates to sin 2jx upon 2, but when I put the limits minus pi to pi, it is 0. So what survives is the first term. So you get pi aj minus aj by 2 into 2 pi, that becomes 0. So we have verified that fx minus Snf is orthogonal to cos jx, and this is true for all j equal to 1, 2, 3 up to n. Similarly, you can check that fx minus Sn fx is orthogonal to sin jx for j from 1 to n. It is also orthogonal to 1. So we have proved that fx minus Sn fx is orthogonal to 1 cos x sin x etc. cos nx sin nx. In other words, it is orthogonal to every linear combination thereof, and so it is orthogonal to Rnx. So now we can apply the Pythagoras' identity, and we get norm of fx minus qnx squared equals norm of fx minus snx squared plus norm of Rnx squared. Now notice that norm of Rnx squared is always non-negative. So what do you get? You get that fx minus qx norm greater than or equal to fx minus snf norm. So f minus snf norm is less than or equal to norm of f minus qnx. That's exactly what we are supposed to prove. When will equality hold? Equality hold if and only if Rn is 0. But what is Rn? Rn is what? Rn is exactly Snf minus Qn. In other words, equality holds if and only if Qnx is Snfx. So this is a principle of least square approximation. Of all possible trigonometric polynomials of degree at most n, the partial sums of the Fourier series of degree at most n is the best approximation in mean. So now let us get to the next important theorem, which is the Bessel's inequality. So what do the Bessel's inequalities state? The Bessel's inequality states that if a0, an, bn, n equal to 1, 2, 3 are the Fourier coefficients of a function f in L2 of minus pi pi, we have the following inequality: mod a0 squared plus 1/2 summation n from 1 to infinity mod an squared plus mod bn squared less than or equal to 1 upon 2 pi integral minus pi to pi mod fx squared dx, which is equation 2.4 in the slide. So let's start the proof without any delay. We have already seen that 1 cos x sin x etc. are orthogonal to fx minus Sn fx. That is, fx minus Sn fx is orthogonal to all trigonometric polynomials of degree at most n. And so let us apply Pythagoras' theorem. In particular, fx minus Sn fx is orthogonal to Sn fx. So let us apply the Pythagoras theorem now, and we get norm fx minus Sn fx squared plus norm of Sn fx squared equal to norm of f squared. From that we immediately get norm of Sn fx squared less than or equal to norm f squared. Now let us calculate the left hand side of 2.6 in detail. Let us calculate norm of Sn of fx the whole squared. So what are we supposed to show? We are supposed to integrate from minus pi to pi. We are supposed to take a naught plus summation j from 1 to n mod aj cos jx plus bj sin jx the whole thing squared. So just expand it. We get mod a naught squared integral, and then we will get integral of mod aj squared cos squared jx. We will get integrals of mod bj squared sin squared jx, and then we will get the cross terms 2aj bj cos jx sin jx integral minus pi to pi, that is 0. So which terms survive? The mod a naught squared, mod aj squared cos squared jx, that will give you a non-zero integral, mod bj squared sin squared jx, that will give you a non-zero integral, etc. We get norm of Sn fx squared equals 2 pi times norm of a naught squared plus pi times summation j from 1 to n mod aj squared plus mod bj squared. The inequality norm Sn fx squared less than or equal to norm f squared translates to mod a naught squared plus 1/2 of summation n from 1 to n mod an squared plus mod bn squared less than or equal to 1/2 pi integral minus pi to pi mod fx squared dx. Now we simply allow n to go to infinity and we get the desired result, and the proof of Bessel's inequality is complete. It turns out that the Bessel's inequality is actually an equality, and that is theorem 18, and this theorem is called the Parseval formula. Suppose f is in L2 of minus pi pi, then 1/2 pi integral minus pi to pi mod fx squared dx equals mod a naught squared plus 1/2 summation n from 1 to infinity mod an squared plus mod bn squared, equation 2.7. Formula 2.7 has a very simple physical interpretation. We should think of our function f of x as a 2 pi periodic signal, and the integral that you see on the left hand side 1/2 pi integral minus pi to pi mod fx squared dx is the average energy of the signal. It is the energy of the signal. So what the equation says is that to compute the energy of the signal, we simply have to look at the contributions from the Fourier coefficients. The constant coefficient contributes mod a naught squared, and the components of frequency n, cos nx and sin nx, their coefficients are an and bn, and they contribute to mod an squared by 2 and mod bn squared by 2, and you simply add the contributions from each of the Fourier components and you get the total contribution to the energy integral. We will have to do some work to prove this equation 2.7. We will need the Fayer's theorem. So we shall prove this after we do the proof of the Fayer's theorem. So we will continue this in the next lecture.